It's 11:02. Let me see if I can share my camera. Okay, that's fine. Well, welcome everyone. Thanks for joining our GPU Accelerated Data Science webinar. In this particular installment, we will be talking about using SQL to process data and query data with GPUs in Python. So we're going to start with a very quick overview of BlazingSQL and Rapids, and then we're going to do a hands-on session on running some queries on BlazingSQL, and at the very end we're going to have some time for Q&A. So let's get started. BlazingSQL, what it is. BlazingSQL is a SQL engine that runs on top of cuDF data frames. cuDF data frames or Dask cuDF data frames in case of if you run your queries in a distributed way. It's a very simple interface that allows you to quickly create tables on top of a cuDF. Like in this particular example, we use cuDF to read a CSV, sample taxi CSV file, and then create a table on top of that by passing that cuDF data frame to the create table call. And then once we registered that table with the BlazingContext, we can run SQL queries on top of that. And in this particular case, we just simply count how many rows we have in that particular data set. How does it fit into the whole Rapids ecosystem? So BlazingSQL, as I mentioned, is a distributed SQL engine that is part of the Rapids ecosystem. Rapids is the end-to-end data science stack that runs almost entirely in GPUs, pretty much entirely in GPUs, unless you really need the data back in the host memory, then you can just bring it over. But everything that you run with Rapids executes on GPU, and same goes for BlazingSQL. Any call to BlazingSQL will execute on the GPU. If your data doesn't fit on a single machine, or you need more processing power, you can use Dask to distribute that to hundreds, if not thousands of machines that are fitted with GPUs. And it can be both machines that have a single GPU in a box or multiple GPUs in a single worker. In terms of the distributed data science stack, BlazingSQL sits on top of CUDA and CUDA libraries. We heavily use the underpinnings of cuDF, the C++ side, and also storage plugins. Storage plugins are shared between the cuDF and the BlazingSQL itself. We use Apache Calocyte to parse the SQL queries and create this relational algebra that then gets executed using CUDA kernels. All of this happens, and the interactions with the BlazingSQL engine happen through the Python layer. We use Cython to convert the Python calls to run on a CUDA. If you need distribution, you can use Dask, and Dask facilitates the communication between workers. Right now, we support TCP, and UCX is in an experimental stage. In the whole Rapids ecosystem where BlazingSQL sits roughly around the ETL stage, same as cuDF. And any call to BlazingSQL engine that starts with bc.sql will return a cuDF, a data frame, or a Dask cuDF if you run on a Dask cluster. So we kind of help each other, right? So BlazingSQL and cuDF, they go hand in hand. If things are easier to do using SQL, you can use BlazingSQL. And then the cuDF data frame that you can get back, if things are easier to do using the Pandas-like API using cuDF, you can very easily do it that way. Then we go to the model training. You have the access to QML, which is the machine learning library from Rapids, or cuGraph if you want to do graph analytics. Or if you are inclined to do so, you can do pass the cuDF to a deep learning like PyTorch, deep learning framework like PyTorch or Chain or MXNet to build a deep learning model. In terms of visualization, you have access to Q-cross filter or Q data shaders, so you can visualize your data, pretty much staying constantly in the GPU memory. What actually facilitates all of this seamless interaction between all of these components is the Apache Arrow project. So everything in the GPU memory is an Apache Arrow object, and BlazingSQL or QDF or QML can directly read those objects and then work on them without the necessity of converting and transforming the data between different representations in memory. So in a very, very simplistic example, very simple example here, we have our data that can be in almost any format. In this particular case, it's a CSV, Parquet, ORC, Pandas, QDF, or whatnot. And these files can be either local to your machine or can be sitting somewhere in the cloud. In this particular case, we are reading and registering an S3 bucket, AWS S3 bucket called BlazingSQL, BSQL, with the BlazingContext, create a table from a remote repository. So in this particular case, it's S3 BSQL TPCH SF100 orders. And then automatically, just like that, we can start running SQL queries against that table, the orders table. Once we're done, the feature engineering is done, the ETL part is done using BlazingSQL or QDF, whatever is easier for you. You can head it over to the machine learning. In this particular case, we push it on to XGBoost, but it can be any machine learning algorithm that is available in QML. And QML keeps growing both in the feature richness and also the speed. So how do you get started with BlazingSQL and Rapids? There's two ways. You can do an open source way. It's very easy. You can go to Anaconda and then just simply install that directly from Rapids channels or BlazingSQL channels. You can go to and download a Docker image and run it in a Dockerized form on your machine. Or on the other hand, as we will do today, you can use this pre-built turnkey BlazingSQL notebooks offering that allows you to, today we are going to use this free offering that we offer to you, where you can start running BlazingSQL and Rapids queries directly in the cloud. And if that's not enough, we offer a private clusters where you can spin up clusters anywhere between 1 and 64 GPUs. These are dedicated GPUs, and then if your data requires or you require more power or distributed way, you can go down that path. In terms of the Rapids on the cloud, this is pretty much the interface you would be seeing. You can create clusters. These are all private GPU clusters. You purchase credits. Every credit gives you 1 hour of compute on a single GPU. So without further ado, let's get cracking. So before we go to the app.blazingsql.com, as I show you here, let's go through what we need to do first. If you're joining us for the first time, you don't really need to go through all of these steps. You go to the app.blazingsql.com, log in with your Google credentials, and you should be ready to go. If you had attended any of our previous webinars or you have used app.blazingsql.com before, you might want to wipe out the Welcome to BlazingSQL Notebooks folder first. So we're going to go through that in a second, and then just git clone the repository again, so you have the access to all the notebooks that we will go through today. So let me switch the gears now, and I'm going to switch to the Jupyter Lab that I already have running here. I'm going to stop that and restart my server. So you go to app.blazingsql.com, and what you should see is pretty much Jupyter Lab. So let's open a terminal first, and I am going to wipe out my Welcome to BlazingSQL Notebooks folder first. Welcome to BlazingSQL notebooks first. And then I'm going to go to GitHub to Blaze. I'm going to paste this into the chat window. Where's the chat? Chat, there you go. I'm going to paste the link over there so you guys can go ahead. I am going to clone that. So I'm using HTTPS, clone this. And then I'm going to do git clone, paste that, and check out that repository again. So I get the latest list of all the notebooks that we have over there. I can see it showed up there. We're now checking out the files. And in no time, we should be up and running. Alrighty, so this should have opened up. So now navigate to Welcome to BlazingSQL Notebooks. Go to Webinars, Rapids Intro, and over there, you should see the 03 notebook, 03 Introduction to BlazingSQL. So let's open that up. I'll make it smaller and make this a little bit bigger. All right. So we are going to use this notebook today. First things first, as always, we need to import all the things that we're going to use today. So we're going to import QDF, we're going to import BlazingSQL, S3FS because we're going to be reading data from a remote, from our S3 bucket. We're going to be using NumPy, collections, and so on. So I'm going to start and execute that. That might take a little while because it's importing everything. There you go. We're done there. So first things first. As I mentioned before, the entry point to BlazingSQL is BlazingContext. So the BlazingContext is effectively this Uber context that allows you to create files, create tables, connect to a Dask cluster, drop tables, execute SQL queries, explain the SQL queries, and so on and so forth. So in this particular case, we are starting BlazingContext with no external parameters. So with all the parameters set to default, I'm going to start running that and I suggest if you follow me hands-on, I would suggest you start doing that right now. It might take some time, so don't get discouraged if it takes 1 or 2 minutes. The first time you run it, it takes a little bit of time. The next time you run it, it takes literally seconds. As I mentioned, we are starting the BlazingContext with default parameters, but there's a bunch of options that you can specify. You can specify the Dask client. So the Dask client, if you have a Dask cluster running somewhere, and it has access to, and is running on a cluster that has GPUs, you can create a Dask client against that Dask cluster and pass that Dask client to BlazingContext. That way you get access to all the goods that are available to you by using Dask. So you can distribute your work. You can run your SQL queries against the data that is distributed. So it's going to enable you to tackle much bigger problems or run these queries much faster. The allocated argument here allows you to specify the unified virtual memory. So it allows you to specify whether you're going to use the Rapids Memory Manager or something else to execute your queries. And also by using the allocated, it defaults to managed. It allows you to spill. If your data doesn't fit into the GPU memory, it allows you to automatically spill whatever is not fitting into the GPU memory to your host memory. You get a performance hit that way, but that allows you to actually tackle much larger data sets, even on a GPU that is, doesn't have that much memory. Enable logging, it allows you to, as it says, enable logging as well. The initial pool size, this is a performance tuning parameter. So it allows you to preset or initialize a memory pool on your GPU to pre-allocate that and then pass it on to the Rapid Memory Manager. That allows you to quickly get this performance boost, right? So if you have a GPU with, let's say, 24 gigabytes, it allows you to pre-allocate, let's say, 12 gigabytes, and automatically all of that memory is allocated and only used by BlazingContext. And that way you don't get the performance hit when you need to allocate and deallocate the memory later on. That is only going to take effect on the BlazingContext if you set the pool parameter to true. You can also specify the network interface. In this particular case, if you're running, for instance, a image on AWS, you might specify ENS5, or if you're running things locally, you can specify ETH0 and so on and so forth. You don't really need to do it if you're running that on your local machine. So it defaults to Ethernet 0. And there's a bunch of other configuration options. I would suggest you go to docs.blazingsql.com and you can look them up over there. But now that we have the BlazingContext ready, we can start playing with the data. In this particular case, we are going to be using some data from the air transportation. Specifically, this is a data that we collected from I believe, the Bureau of Air Transportation. And it lists all the flights that departed and whether they departed on time, what equipment they were using, and so on and so forth. So this data sits in our S3 bucket in BSQL. And in this particular case, we're going to use the first 5 months of 2020. The idea here is to compare whether the COVID pandemic had any effect on flight punctuality in overall. So we're going to use the S3 file system to list all of the files that we have over there. Be mindful that you need to pass the ANN equals to true over there, because this is a public repository. We don't require authenticating with the bucket itself. But if you don't pass the ANN equals to true, it defaults to false, and S3 file system will require you to pass some credentials, which we have none, so that will lead to some problems. Let's see what kind of files we have over there. We have 5 files, as I mentioned before, January to May of 2020. So in terms of if you were to read that into a QDF, QDF cannot read multiple files at a time. So what we do here, we read one file at a time, and then we append that to a list that we later are concatenating using QDF concat call. So we pass the QDF read parquet one file at a time, and just like before, we need to pass the storage options ANN equals to true. So the S3FS underneath the hood doesn't try to authenticate with the bucket itself. So let's run that. Shouldn't take too long, even though this is a remote storage. Shouldn't take longer than a couple of seconds. And then let's peek inside into the data that we have over there. And then we can actually execute the next one as well. See how many flights we have in this particular data set. That must be a little bit something happening on the AWS side, because that's normally, it doesn't take that long. We have some time. While this is running, I might shift gears and start talking about BlazingSQL. So now that we have our BlazingSQL context ready, right? If you want to read the data from a remote location like S3 bucket, in this particular case, we are going to simply register the S3 bucket with our BlazingContext. So the BlazingContext is aware that there is some location, remote to me, i.e. the context, that is called BSQL on S3. And we're going to alias that as also as BSQL so we don't get confused. Note that here, I do not know what happened. So let me restart that quickly. Yes, leave that. There must be something really happening on the back. Okay, let's try that again. Going to log in with my credentials. And let's quickly restart that. Okay, so I'm going to restart the kernel and clear all the outputs and quickly get to the same point as we were before. Okay. I apologize for that. I'm not entirely sure what's happening today with this. Okay, let's try to restart that again. There we go. All right, so now this should be ready to go. Let's run the BlazingSQL context. First, the imports. Yeah, the first time we run it, it might take a little bit of time. That's the AWS spinning up all the resources behind the scenes for us. All right. Oops. All right. While this is running, I am going to execute all of these that we already had so far, all up the way to here. So we were talking about registering an S3 bucket with BlazingContext. So right now, what you can do is to literally create a table on top of those, on top of that bucket. So we are reusing the files that we've listed here, and we just simply pass them as a parameter to the create table, air transport table, right? So once you create this table, you have effectively created a representation of all the data that sits in those files, and you have the access to that the data by calling the by the means of the air transport table here. So I'm going to start running this, then register the table here. So now that you have registered the table with the BlazingContext, you can start running SQL queries against that, right? You can do select star from air transport limit 5, which is effectively an equivalent of .head 5 if you were to run that on a QDF, just like over here, right? So this is the simplest way to get started with this is probably the hello world from the SQL world, right? Let's see. Okay, that has imported. So right now we are creating context and we should be good to go soon. So I'm going to start this, executing that. And then just like we did with the total number of flights in this data set by taking the length of the flights QDF, the data frame, we can do the same thing with the BlazingContext. It's a little bit more convoluted example, but we have BlazingSQL select count star as count from the air transport table, extract the count column from that QDF that gets returned, and then take the first row from that QDF. So that should give us the same number. This is taking a little bit longer today than I expected. I'm not entirely sure what's going on, but I'm pretty sure once this is created, we should have the Blazing log there. Okay. I'm going to continue, and we can come back to that. Later. So columns and data types. Just like if you had attended our QDF introduction to QDF, you can get the columns, the list of columns from QDF by simply calling the attribute.columns. And if you want to see all the data types that are associated with these columns, you just call the types. As I mentioned before, the BlazingContext returns a QDF data frame. So we have pretty much access to the same API. There we go, finally. All right, we're back in business. As you can see, it takes 4 seconds to read all of those files from a remote file. And this is what the data looks like underneath. So we have the year, we have the quarter, month, day of the week, the flight date, the unique marketing carrier, and the flight number, and so on and so forth. And also at the very end, we have all of these information about delays. So you have the information about the air time, we have the actual lapse time, CRS elapsed time. CRS is the computer reservation system. So when airlines schedule their flights, they put an estimated flight time, elapsed time there. So you can see directly from this that this flight was delayed by roughly, I think, if my math's right, 27 minutes. Well, yeah, there you go. So you have 27 minutes delay. And you can say, you can see why it was delayed. So in this particular case, it looks like the aircraft arrived late. So that's why it trickled down into the delayed flight before. In this particular data set, we have 2.5 million flights. So this is 5 months of 2020. And exactly the same thing, if we run select count star from air transport table, we get exactly the same number. So you can do it with QDF by running len, or you can do it with BlazingSQL by running select count star as count. So now let's look at the columns. There's lots of columns in this particular data set. So you can see we've seen year, quarter, month, day of the week, and so on and so forth. You can see whether the flight was canceled, whether it was actually delayed. There is a arrival time. There is the departure time. I'm looking for one. Arrival delayed. OK, let's check the data types. So you can see that year is int64. Flight date is actually a string. So that's definitely something that probably even 3 to 4 years ago, nobody would have thought that it was possible to play with strings on a GPU. But right now, thanks to Rapids, we actually can. We have the departure time, departure delay. That's what I was looking for. This is a column that tells you whether the flight was delayed or not. So it can have a negative numbers there. It's float 64. So if the flight departed before it was scheduled to depart, you would have a negative number here. If it departed right on time, the departure delay would be 0. If it was delayed, this number would be positive. And you can have you have access to all of these additional metadata. So when the wheels were off and on, back on the ground, how long it took to taxi in, what was the arrival time, arrival delay, and so on and so forth. And the same thing you can actually achieve by running the Blazing stuff with BlazingContext. So you can select star from the air transport. I would highly suggest you don't do select star from air transport without the limit or sample at the end, because that will effectively collect everything that you have stored in the memory. If you run it in the distributed way, it will collect everything, all the file, all the information from all the workers that you have, and then return that back to your host, and it most likely will break that host. So you can see, as I mentioned before, every call to BlazingSQL returns a QDF in this particular case, because we're running on a single machine. So you can see, check the type of the BCDF, and it indeed is a QDF data frame. So with that, we have access to exactly the same API. You can call the columns, you can call the data types, and so on and so forth. and I get exactly the same return as you would have to if you were to use the pure pandas-like CodeEF API. We also supplement all of this information with some metadata about airports and airlines. They all sit in our S3 bucket as well. So airports path and airlines path are listed over there. In this particular case, because we are running the information, the information is stored in a CSV, it's better to specify the data types and the column names, even though we might have those already in the file itself. In this particular case, these particular files are actually headerless, so it's good to pass the names and D types to read CSV call in order to specify the column name and the data type. So we're going to run this airports. We have the airport, we have the IATA code, which is the international standard for calling those airports, to coding those airports. ICAO is used mostly by pilots. It differs a little bit. We have the Latin longs, the altitude of the airport, and so on and so forth, and the time zones. In terms of airlines, we have the airline ID, airline name, the alias, the IATA call sign, and the ICAO code as well, and then where the particular airline is registered. So United States, South Africa, United Kingdom. And then as we did before in the very short example in the deck, we can now create tables on top of those CodeEF file data frames. So simply run that, and we're good to go. So SQL allows you to very, very easily run queries against your data, right? So in this particular case, what we try to do is to collect all the interesting information into single queries. So we are going to extract all the flight dates and the unique carrier's carrier name. So that carrier name comes from the table B, which is we are left out adjoining from our air transport. So we take all the rows that are in the table air transport, and then look up the IATA code from the B table, so which is airlines, based on the unique carrier name, so carrier code. So we join on these two tables, and whenever we can find the record in the right-hand side, i.e. in the airlines column, we can extract that information, extract that column name from that B table there. And same for the origin. So we actually going, instead of the airlines, so we go to airports. We also join on the IATA, and then origin. Origin is the originating airport. In this particular case, we are going to take the origin name and the city as metadata from the C table. And then for the destination, we join again to the same airport's data to extract the information about the destination. So let's run that. Remember, this is joining 2.5 million rows on one hand side, which is all the flights, and roughly a couple of thousands on each side on the other side, so for airlines and airports as well. And there you go. You have the flight date, February 9th, Pinnacle Airlines departed from Lovell Field in Chattanooga and was heading to Atlanta for the Hartsfield-Jackson Atlanta International Airport. Now, what we did here, we actually created the tables from the CodeEFs. We read the information from CSV files first and then created tables on top of that. You don't have to do this. So with the BlazingContext, you can create a table directly from those files. You can push the airport's path. This is a CSV, as you can see over here. This is a CSV, just literally a string, right? And then specify the same parameters as you would do with the read.csv. So we pass the names and the dtypes parameters to create table, and BlazingContext will literally do this. So let's run that. And then as you can see, right now we can join with the airports table, and I think this should be table. And then if you run this, you get pretty much exactly the same result, right? So we have, it's going to be sorted differently, but you get the same, the same information. Is it easier or is it harder? It's hard to say than using QDF, right? So you can, this is an equivalent of this table as if you were to use QDF API, so pandas-like API. You can merge, you merge airlines IATA name left on, so which is exactly an equivalent of pretty much this call over here. You have joining on airlines IATA name and left on unique carrier right on IATA, which is pretty much this. Then we're dropping the IATA because the IATA from the airlines is not the same as from the airports. So now we are joining into the airports. We bring over IATA name and city because this is the names we're going to use here. And we joining on the origin name, origin and IATA, then renaming those names. So this call over here is effectively this particular alias here in the SQL world. We drop the IATA and then merge again to the airport in order to extract the metadata about the destination. What's simpler? I'll leave it up to you to answer if you're so inclined. For these types of operations, I prefer to use SQL because it's more readable for me and it's less, I don't need to type as much. If you prefer this way, if you come from Pandas world, that's also doable. And as you can see, if you run that, you'll pretty much get exactly the same result with slightly additional, additional things in there. I don't think we carry we do have origin. It's just I think reshuffled a little bit. The order of columns is different, but you get pretty much the same information. So if you were to run queries against this data frame, you'd get exactly this access to the same information as before. So now that this is out of the way, we can start asking questions against those tables. So we can ask like how many unique airports do we have in this data set? And in this particular case, we are going to use only at the origin. And if you are to use the QDF, in this particular case, I prefer using QDF because that's much easier for me to just literally take all the unique values from the origin column and then run the length, to get how many airports do I have in that data set. So in this particular case, we have 371 airports in this particular data set. The equivalent call in the SQL world would be something like this. And you can see that it's much more verbose than the previous one. I like to be succinct. So you can do it using QDF, but the results are exactly the same. 371 distinct airports in this data set. I like to use the tools that actually allow me to get what I need and get what I want as quickly as possible. I know I can do it both ways, but I just simply prefer this way. So now we can check. So the Uber questions that we might ask about flights, and in this particular case, would be how many flights were delayed, right, or departed early, and because what we want to ascertain is effectively when the pandemic, the COVID-19 pandemic hit, has it had any influence on whether the flights were delayed or not? So let's start pinning off that particular onion and then see what we can find out. So let's see first. Out of our 2.5 million flights in this particular data set, 500,000 were delayed, right? 500,000 were delayed, and 1.7 million left on time or early. So you can see that the flights, the departure delay is greater than 0. That's our call to determine whether they were delayed. and less than or equal to 0 if they left on time or early. So we have 500,000 there. So let's see, let's calculate the distribution of these delays. So the first delays, first we're going to specify, okay, we're going to bin all of these departure delays into 100 bins. And let's separate delays from the on-time flights. So this particular call here allows us to do that. We can actually, let me add file here and then pick inside delays head. This is what we currently have. So this particular call over here will effectively just extract the departure delay column from our flights QDF, and it will help you. It will give you the series. So one column in every single QDF file is a series. So right now, what we can do is create our bins. In this particular case, we are going to bin the departure delays into 15-minute buckets, up to 100 buckets like that, and use the digitize call from QDF series to actually take our departure delay and then assign it with the proper bin. And then to create the histogram itself, we are going to use group by and count how many how many flights fall into each particular bin. So let's run that. And there you go. Most of the flights actually are delayed. So roughly 50% are delayed anywhere between, they either depart on time or are delayed by 15 minutes. So we do the same thing for the on-time bins. Let's check. But in this particular case, we actually create the bins that are 1 minute width. So let's do the same thing. And you can see that if the flights depart, they mostly depart on time or around 5 minutes early. It's a long tail, of course, but you can see that rarely any flight departs, anywhere between 20 minutes early. So if you get to the airport, you are more likely to actually depart on time or be delayed rather than depart like 20 minutes early, so that they will wait for you anyway. And so next question we can talk about is, okay, so now that we know that the flights depart delayed, there were some flights that actually departed, 3, 4, 5 hours delayed. So if you look at this particular, chart, you can see that there were still flights that were 2 hours delayed, right? Or 1 hour and a half delayed, or 1 hour and 45 minutes delayed, and so on and so forth. So let's look. Is there anything that we see in terms of the destinations, right? So if the airport, if they fly to, where do they fly to, or where do they originate from, that you have the highest chance of getting delayed? So we are going to actually create tables of our delays and on-time QDFs and create a table. So now we can use BlazingSQL, because that might be much easier for us to achieve. So we are going to select the origin. In this particular case, we are flying somewhere, right? So this tells you, this answers the question that, like, okay, if I am in Seattle, am I likely to get delayed or not, right? So we are going to look at this particular data set, delays, and then count how many flights were delayed and what was the average delay in this particular data set. We are only looking at flights, the airports that had at least 1,000 flights, 1,000 departures that happened between January and May of 2020. And we are going to order that by the average departure delay, which is this particular column here, in a descending order. So we want to have those mostly the most delayed airports at the very top. We're going to take 10 top 10 from this. So as you can see, we have the Norfolk International Airport in the United States, which had 1324 flights that were delayed. And on average, these flights were delayed by 55 minutes. The next one is Savannah. The next one is Charleston. And then we have Washington Dulles International Airport with almost 4,500 flights that were delayed during this period of time, and an average delay of 50 minutes. So, okay, well, Seattle is not there. I'm glad, because when I travel, I don't need to be too worried that I'm going to get stuck at the airport, unable to fly out. Now, let's look at the destinations. Per destinations, where do people normally travel that they get delayed the most? So Chicago, O'Hare, with 22,000 flights, and average delay of 55 minutes. So if you fly to Chicago, you are quite likely to get delayed, probably no matter what, where you're flying from. Newark is another one. Washington Dulles is another one. So it looks like the Washington Dulles, you can get delayed both when you fly in and fly out from Washington, D.C. Same with Savannah, as you can see over here. So now let's check, is there any airlines that are more likely than others to be delayed? So we have the Commute Air that in that particular period of time, 3,900 flights that were delayed with average delay of 70 minutes, sorry. Air Wisconsin follows that, Trans-States Airlines, GoJet, Gandalf. So it looks like it's mostly the smaller airlines that get delayed, with an exception of SkyWest that had 49,000 flights that were delayed, roughly on average 55 minutes. Comair is another one that had 22,000 flights in that particular period of time. So these are the delays. Let's see, okay, if you don't want to get delayed, should you use fly from somewhere else, or where would you fly when you normally would expect to be on time? So in terms of the least delayed flights, and these are the origins. If you fly out of Dallas, there were 15,000 flights that were actually departing on time, mostly on time. So they were departing on average 4 minutes early. And then Houston, Chicago Midway. So if you fly to Chicago, fly out of Chicago, you are more likely to have least delayed if you fly out of Midway. Atlanta is another one. So there was 81,000, almost 82,000 flights out of Atlanta, and they were delayed by, they were departed 4 minutes ahead of time on average. Okay, so let's look, if you fly, where you fly to, that you might expect to be mostly on time. Houston shows up again, so 12,000 flights in this particular data set that departed on time, and 4 minutes. Chicago Midway again, so if you fly in and out from Chicago Midway, you might be expecting that you'd normally be on time in this, at least judging from this particular data set. And then in terms of airlines, let's see which airlines are the most punctual. It looks like Southwest is quite punctual. Delta, Spirit Airlines, Horizon Air, American Airlines, and so on and so forth. So if you choose to fly with the bigger airlines, you are more likely to depart on time or slightly ahead of time. So now we've mentioned that with BlazingSQL, you can operate on strings, and with QDF, you can operate on strings as well. So in this particular case, we are going to actually convert the flight date, because it's an object, to a datetime 64 type, and then extract the year, month, day, and the day of the week. We all do this because even though we already have this information in the data set, but we can still just to showcase how this is done. So now what we can do, let's see how many flights per month were there at the very beginning of 2020. So as you can see, right before the pandemic hit, January, February, and March, there was still a lot of flights departing. But as soon as the country and the world started to shut down, you can see that the number of flights quickly went off the rails. And then in April, we had literally roughly half of what departed on in March, and then even less in May. So let's see, in terms of the day of the week, do we see any seasonality here? It looks like pretty much throughout the whole week, the number of flights that departs is similar. If my memory serves me right, 0 is Sunday. So Monday, Tuesday, Monday, Tuesday, Wednesday, Thursday, Friday. On Saturdays, you have less flights. So most of the flights, and then the biggest traffic happens during the weekdays, right? So the business week, and then Saturdays there's less business traffic. So you normally would expect that you would have less flights over here, and then Sundays the business traffic comes back because during the night that people will start, flying where they need to fly to start the week already at the destination. So have some time over there. But this is pretty much it, what we have in terms of the introduction to BlazingSQL. As you can see, that it's super easy to work and change shoes. If you run BlazingSQL, or you are more familiar with QDF, or you want to mix and match, whatever you feel that you can achieve things you set out to achieve easier, you can use either SQL or you can use the Pandas API to achieve that goal. And it's super easy. So right now, today, we've been using the BlazingSQL.com. Whenever you come back to BlazingSQL.com, you can start your own server and then run the queries. This is free of charge. If you don't have, if you need more power, if you need more, your data doesn't fit on a single machine, you can go to beta and request access to our beta offering from BlazingSQL, and then you can create private clusters. This is the interface that we have. We support different environments, so you can create your own environment. You can create, if you use some additional packages that we currently do not carry in the main image, you can add them on via either just creating a YAML file, just like Conda, and then create your cluster on top of that. Creating cluster is super easy. You just put a cluster name. You select the size. So you can create a cluster from anywhere between 1 GPU to up to 64 GPUs. I forgot to mention that all of these GPUs are T4s that we run on AWS, and all of them come with 16 gigabytes of RAM. In case you forget to turn off your machine or turn off your cluster, right? And running GPU clusters is not cheap. We automatically can shut it down for you, depending on how long you want us to wait to, after you finish your work. So you have the choice to close it off by yourself. That's the easy way. But if you forget, it happens. 5 minutes later, we'll shut it down for you, so you don't get charged, for stuff that you don't use. And as I mentioned before, you can use, specify the environments. Right now, by default, we use Rapid Stable and Rapid Nightly. But you can create your own environments by just going here and then create an environment. You paste the YAML file here from that, as you normally would create a Conda environment, and you off to go. Very good. That's it from me. So let me check if there's any questions that we have. I don't see many questions, but if there's no questions right now, or you're watching that on demand after we've on YouTube, because this is a stream session, by all means, either find me on Twitter. My alias is @TomicDravas, or shoot me an email at tom@blazingsql.com, and I'll do my best to return, to return any questions that you might have. But if I don't see any more questions, I think we can stop right now. Stop here. Thank you everyone for joining or watching us live on YouTube, and we hope to see you. We hope to see you in 2 weeks. In 2 weeks, we're going to do introduction to distributed computing with Dask, and our guest from NVIDIA will be delivering that particular webinar. So thank you very much, and all the best trying using BlazingSQL on app.blazingsql.com or locally on your local machine. Thank you.